So again, even if you get rid of, like, maybe you do star 360, but you choose not to come to live sessions, you're going to see that it's going to be really hard for you to get above 90% because if you're not coming to your live sessions, you're missing out on that 10%. Okay, give me a thumbs up if all of that makes sense. If you want to see your grade go up, you need to go to the category that you have the lowest grade in and do work in that category. Excellent. Okay, so we are talking about forces in motion. We talked about Newton's 3 laws of motions. Today we're going to look at the second and third one. So we should be able to explain Newton's second law of motion and complete calculations using force equals mass times acceleration. And we should be able to explain Newton's third law of motion and provide examples of actions and reactions. So Newton's second law of motion says that force is produced by both mass and acceleration. So we've seen this slide before. We've already talked about Newton's first law. We know all about that. Now we're talking about Newton's second law, which is that there's a relationship between mass, acceleration, and force, and Newton's third law. For every action, there is an equal and opposite reaction. So Newton's second law of motion says that in order to cause acceleration, which means a change in velocity, so we're getting faster, we're getting slower, we are starting motion, we are stopping, we are changing direction, any type of acceleration, in order to cause that, there must be a force that acts on it. So that acceleration is going to depend on the force that you apply as well as its mass. So remember, we talked about this yesterday, that if we want to push a hockey puck, okay, if we want to make it accelerate to start moving, two things are important, both how much force you apply as well as its mass. So for example, a puck is super light, so it's pretty easy to accelerate it pretty quickly. But a refrigerator is much heavier. So for a refrigerator, is it easier or harder to accelerate it with the same type of force? Yes, exactly, Mike. Exactly, Alyssa. It's going to be much harder, right? So that's why it's important to take all three of these things into consideration when we talk about forces, mass, and acceleration. Okay, so Newton's second law of motion is actually just an equation which says that a force applied to an object equals its mass times its acceleration, or what you can see right here, force equals mass times acceleration. You do need to know the units, so we measure force using what are called newtons. You'll notice that Newton is the scientist who came up with these laws of motion. Okay, Ariana, that's on your side because you have slow Wi-Fi. Okay, mass is measured in kilograms, and acceleration we learned yesterday is going to be measured in meters per second squared. Give me a smiley face if this slide makes sense. We're going to actually use our equation in a moment. Sorry, Miranda, I put it in the main box. Thanks for reminding me to put it in there. Yeah, I just put the link and the password for the attendance ticket in the main box. Awesome. Okay, let's go ahead and actually do this. Oh, sorry, let's first remind ourselves, what is the correct equation for force? Use your polling tools. At the very top, your green checks have turned into polling tools. A, B, C, or D. Dalen, it's in the chat box. Looking good. All right, and what I see from you guys, I see mostly D's, and D is correct. Force equals mass times acceleration. So as we see, force equals M times A. Awesome. Okay, this is number 1 in your attendance quiz. Please give me a green check when you have number 1 saved. Again, if you don't have your attendance quiz opened yet, you need to open it. Link is right there, password's right there. If you're in the live session, do your attendance ticket. You guys have 20 more seconds. Ready, set. I do want to remind you that, remember, all of the attendance ticket answers are related to the questions on your quiz. So if you feel like multitasking, you can always also have the quiz open at the same time. If you feel like that's too much, don't worry. I give you the quiz at the end of class, and you can finish it right after class as well. Okay, but do keep in mind that the attendance tickets, anytime you see this bright yellow box, you're filling something out in your attendance ticket, but it's also related to the answer on your quiz, to the answers for one of the questions on your quiz. Smiley faces if that makes sense. Smiley faces if that makes sense. Awesome. All right, need a green check from Anthony, Audrey, Dalen, Jasmine, Jeremy, Kim, Steve, Tyson. Looking good. All right, let's keep going. It's okay, Ariana. I was just saying that the attendance ticket also is the quiz answers. Okay? All right, so here's our equation, force equals mass times acceleration, and we have a question here that says, what force is needed on a 5 kilogram box to accelerate it 0.8 meters per second squared? So let's take a look at this. Let's annotate what we've got here. 5 kilograms. 5 kilograms here. Is this going to be our force, our mass, or our acceleration? What does kilograms tell us again? What does kilograms tell us again? Yes, this is going to be our mass. Absolutely. Good. And what about 0.8 meters per second squared? What? Oops. Sorry, baby just pushed my arm. What is that right there? What is this going to be? Yes, this is our acceleration. Absolutely. So we know these things. We're going to go ahead and plug them into our equation. So underneath M for mass, we are plugging in what we annotated up there, 5 kilograms. Underneath acceleration A, we are plugging in what we annotated, 0.8 meters per second squared. And plug that into a calculator, please. Again, if you need to, you can Google the word calculator and a calculator will pop up. I need to know, what is 5 times 0.8? Get that up there for me. If you remember the units, extra brownie points for you. If you remember the units, extra brownie points for you. Again, remember the scientist that we are currently talking about his laws. Nope, not meters per second squared. That's acceleration. We're talking about a force. Talking about a force. There we go. I see Vega. Yes. Vega's the first one to get it. Absolutely. Yes. 4 newtons. N 4 newtons. You can put 4N or 4 newtons. Perfect. Now we can rewrite the force equation. And we can rewrite it, we can rewrite the force equation in order to solve for acceleration. So the way that we do this is, let's say we want to solve for acceleration, then we need to get rid of anything around acceleration. So what letter is currently next to acceleration that we need to get rid of? Let's say we want to solve for acceleration. What letter is next to acceleration? Yeah, the M right now is next to acceleration. And if it's being multiplied, I need to do the opposite. And how would we do the opposite of multiplying? We want to get rid of the M. To get rid of it, we do the opposite. Yeah, we're going to divide by the mass, right? So I'm going to divide by the mass. Sorry, I'm going to divide by mass on this side and divide by mass on the other side, because you always have to do the same thing to both sides. Okay? Now, on this side, on the right side, since that's what I did to get rid of the mass, I can just get rid of that completely. Okay? Smiley faces if that makes sense here. We're left with acceleration now. Okay? We got rid of the M, that was the multiplying by M, by doing the opposite, which is dividing by M, and we have to do it on both sides. So what we end up with is acceleration on one side, just like over here, and force divided by mass, just like we see on the other side. Okay? Here you go, Jasmine, in the chat box. Yeah, you don't have to super understand how we got to this part, just know that this equation works. I'm just trying to prove to you that this equation is still the same equation, just written in a different way. Okay? All right, so let's say, for example, that we have a 10 kilogram ball and we want to accelerate it by using a 6 Newton force, and we want to know how much will it accelerate. So let's annotate this. 10 kilograms, what does that tell me? What does kilograms tell me? Acceleration, force, or mass? Yep, it's going to tell me mass, absolutely. And what about 6 newtons? What does that tell me? What does newtons tell me? That's the unit for what? Yes, this is the unit for force, exactly. So let's plug this in. Underneath F for force, I'm plugging in 6 newtons. That's what we annotated at the top. Underneath M for mass, I'm plugging in 10 kilograms, because that's what we annotated up here at the top. And now let's put that into a calculator. 6 divided by 10 will give me what? Please put some units on them. No naked numbers. Put some clothes on those numbers. Oh man, so many naked numbers. They're so embarrassed. Put some clothes on them. Awesome. I see an answer from Vega with units. I see the correct numbers from Theodore and Alyssa. I see a bunch more people typing. Get me your answers. Excellent. Yes, you guys are doing awesome. 6 divided by 10, if I plug it into calculator, absolutely equals 0.6, and our units should be meters per second squared. Okay, give me a green check if you feel like you're comfortable with this. You understood what we did here. All right, let's keep going. Okay, so here's another term that we need to learn, and the term is momentum. So if we want to change the way a moving object is moving, change its direction, we need to be able to overcome the object's momentum. And so momentum just means how difficult it is to change motion. Okay, so I'm going to write this right here. Momentum is just how difficult it is to change motion. Okay, which we have an equation here. Momentum just equals mass times velocity. We don't really need to know this equation. We just need to know what momentum means conceptually. So we need to know what it means like as a concept. Okay, so here's the thing though. When we have a higher mass, we're going to end up with more momentum. So let's prove that to ourselves. Let's say that I have an object that is 1 kilogram and its velocity is 1 meter per second. Okay, tell me, what would its momentum be if I have 1 kilogram times 1 meter per second? What's 1 times 1? What's 1 times 1? Yeah, exactly. So in this case, we would end up with a momentum of 1, which the units for momentum are kilogram meters per second. You don't really need to know the units because they're kind of scary, but all right, so awesome. So that's 1 kilogram mass gives me 1 momentum. Now let's say I increase the mass. So let's say now we've got 2 kilograms of mass. Now what would this be? 2 times 1 would give me what? 2 times 1 would give me what? Yeah, my momentum would increase to 2 kilogram meters per second. What about, let's say I increase my mass by a lot, I increase it to 50 kilograms. Now what do I get? 50 times 1 equals what? Yes, exactly, 50 kilogram meters per second. So do you guys see the pattern here? Every time I increase the mass, the momentum also increases. Do we see that? Smiley faces if we see that. Excellent. Okay, so here's the thing, guys. Your heaviest object, the one with the highest amount of mass, is always going to have more momentum, and it's always going to be more difficult to change its motion. It's more difficult to stop, for example. So a bowling ball has a lot more mass than a feather, and therefore a bowling ball has much more momentum than that feather. Okay? Even in space, where there is technically no weight, so we'll learn this a little bit later, but in space, weight is related to gravity, and since there's no gravity in space, there's technically no weight. However, the object still has mass, because mass just counts for how much matter the object is made up of, the amount of atoms in that object. So again, we've talked about this in the past, that mass and weight are related, but they're not actually the same, even though we talk about them pretty similarly pretty often. Okay? Smiley faces if that makes sense. Okay, even though an object in space has no weight, because there's no gravity, it's still made of something, therefore it's still made of mass. Yeah, so here's what happens. Even in space, objects with more mass still have more momentum. So they're still more difficult to change their motion than something that is lighter, right? So a really heavy spaceship is going to be more difficult to stop than a really light spaceship. Okay, because a heavy spaceship has more mass, it's more difficult to stop. So let me go ahead and show a demo of this to you guys. All right, smiley faces if you can see my video right now. Okay, I'm going to go ahead and set this up really quickly. All right, guys. So do you see here? Okay, let me go out and zoom out a little bit. Do you guys see here? I've got a little ramp and a card at the end. Here, let me look at it from the side. Okay, you see the ramp and the little card at the end. Okay, so here's what we're going to do. Express, there we go. Okay, so I have 4 different types of marbles. Okay, they're all different masses. All right, let me open this really quick. Sorry for my crazy video skills. It's a little bit hard with one hand available. Okay, so right here I've got a tiny, tiny little marble, so very little mass. And what we're going to do is we're going to release the marble from this side, and we're going to see how much it moves the card over on this side. Okay, smiley faces if you understand what I'm doing right now. I'm going to put the marble over here, see how much it moves the card. Awesome. Okay, so here we go. Releasing it. And how much did it move that card? How much did it move that card? Yeah, just a little bit, right? A tiny bit. Awesome. All right, let's go ahead and use a bigger one. So here's our next biggest marble. Yep. Let's go ahead and put that on there. And now we're going to see how much it moves the card. All right, what do we see here? How much did the card move this time? Yeah, definitely a bit more. Good, good. Yep, all right, so here's my next marble. This one's a really, really big one. All right, here we go, releasing it. Let me make sure you get a good view here. And what do we see? It didn't go exactly straight, but what do we see here? Yep, it definitely went quite a lot, yes. And last but not least, here's my biggest marble. Right, isn't this a pretty marble? Awesome, here we go. All right, and releasing it. And what do we see? Yeah. Yep, that card is definitely way gone now. Yeah. Okay, so you guys saw that as we got bigger marbles, what happened to the card? As we got bigger marbles, what happened to the card? No problem, Jenna. Here is your ticket and password. Thanks for making it into class. Yeah, right. As our card got larger, as our marble got larger, the card got moved more and more, meaning it was more difficult to stop the marble. The bigger the mass, the more difficult it was for the card to stop the marble. Okay, so more mass, more momentum, more difficult to stop. So sad. All right, thumbs up if we feel good about that, if that helps you understand what momentum is. Excellent. All right, so let's fill in these blanks together. Even in space, an object with more mass has what momentum? More or less? An object with more mass has what kind of momentum? More or less? What should I fill in here? What do you guys think? Yes, I should fill in the word more mass, more momentum, which means in terms of difficulty, is it more or less difficult to change motion? Yes, it is much more difficult to change motion. Exactly, or to stop it. So for example, right, to stop the spaceship. Okay, so heavier object, more momentum. Awesome. This is number 2 in your attendance ticket. Go ahead and fill those blanks in. Give me a green check when you have it saved. Remember, this question, this attendance ticket item will also be an answer to some of your quiz questions. Here you go, Sayara. In the chat box for you. About 20 more seconds. Still waiting on about half of you to give me green checks. Perfect. All right, let's keep going. Okay, so the last thing that we need to talk about is Newton's third law, which says that for every force there's an equal and opposite force. Give me a thumbs up if you have heard this kind of statement before. Right? For every force there's an equal and opposite force, or for every action there's an equal and opposite reaction. They're pretty similar ideas. Excellent. So we're kind of familiar with it already. So here's the thing, guys. Every single force is going to have an opposing force. So if you are in a rolling chair, or in any chair, for example, what I want you to do is put your hands on the edge of your table and then push forwards, push your hands forwards. What happens to your chair? If you push your hands forward, what happens to your chair? Right, exactly. You pushed forwards, but your chair did the opposite and went backwards. Okay, so there was an opposing force, yeah. So really, you're pushing the table, but the table is actually also pushing you, which is why you move backwards. Smiley faces if that makes sense. If you're laying in a bed, I'm sorry, you're unable to do that experiment. Yeah, good. All right. Now, this is the same thing where, if, for example, if you've ever been in a boat, if you try to jump really far off of a boat, is it easy to jump really far off of a boat? Or off of like a little floaty? Yeah, no, it's not easy to jump far. And the reason for that is because when you jump off a boat, the boat just goes right backwards and you don't get very far from where you originally started. So we can see this right here, that when I try to jump off of a boat, because I'm going forwards, the boat just moves backwards. Okay, and so it's really hard for you to get a firm footing to kind of launch yourself really far from the boat because the boat is just going backwards from you. Okay, and again, this is the same issue that we talked about. An astronaut in space has to be really careful about what they're doing because every action they have can affect their motion. So if they were to have a big basketball, for example, and they were to throw that basketball forward, which way would the astronaut go? If you throw a basketball forwards in space, which way do you begin to move? Yeah, you begin to move backwards, exactly. And so for an astronaut, if they're not tethered to something and they start moving backwards, remember, they're never going to stop moving because there's nothing slowing them down. There's no friction, there's no air resistance, there's no gravity to slow them down. So they have to be really careful with their motion. Okay, so again, Newton's third law, every action there's an equal and opposite reaction, and these forces come in equal and opposite pairs. There's never just one force, there's always a pair of forces that are going opposite each other. Okay, give me an LOL face if this makes sense. LOL face if this makes sense. Awesome. Good, good, good. Why are you guys laughing at me? I'm just trying to teach you. I'm just kidding. All right. So, for example, when we bounce a ball, okay, which was our last lab, so we're kind of trying to tie this back to our last lab. When we drop a ball, the ball hits the ground and then does what? When the ball hits the ground, it then does what? Yeah, it goes back up. And the reason for this is because the ball is pushing on the earth when it hits the earth, but the earth has an equal and opposite force and it's pushing that ball right back. So it pushes the ball right back and the ball goes soaring upwards. Now, the interesting thing to think about is that in reality, the Earth also moves very, very, very slightly. It's just that the Earth has so much more mass or so much more momentum that it's a lot harder to get the Earth to move. So we don't really notice the Earth moving when we bounce a ball. We only notice the ball moving. Okay, smiley faces if that makes sense. Excellent. There are some other equal and opposite forces going on even inside of the ball. So when the ball compresses, when it impacts the ground, it then does the opposite action, which is to expand in order to bounce. So let me go ahead and show you a demo of this idea of equal and opposite. I'm going to go ahead and share this on your whiteboard. Because of gravity, Jenna, right? So we talked about yesterday how the more mass an object has, the more gravity that it has. So you and I have our own gravitational fields. They're just super tiny because we are super tiny compared to the Earth. But the Earth is gigantic, and so it has a really big gravitational field, which keeps things attracted to it. Okay, so here is your link. It's showing up on the whiteboard. If that's not working, give it a few moments to load. Sorry, if that's not working, it's also in the chat box. Open that up, watch that, give me a green check when you have finished watching it. It's less than a minute, so I should see green checks in a minute.
Newton's third law of motion, which says every action has an equal and opposite reaction. It's the principle that sends rockets to the moon. If you want to try this at home, this is what you need. When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction.
All right, green checks please, if we're good on that. Sorry, I'm looking for my phone that's going off right now, but my daughter put it somewhere. There we go. Okay, yes, so this is definitely, it's kind of expanding on the stuff that you've already learned, Ariana, but you do learn some physical science in junior high, which is why it also seems familiar as we are talking about it right now. Cool, all right, so what we saw here is that the balloon, right, the air was pushing out to the left, so which way did the balloon actually move? Yeah, it went to the right, right? Because that is the opposite direction of the force from the air coming out of the balloon. Excellent. Okay, give me a round of applause if that helps you better understand equal and opposite. Give me an applause sign if that helps you understand. Excellent. Good, good, good. Thank you, guys. I'm bowing right now because I really appreciate your round of applause. Awesome. Okay, so Newton's three laws, these are the foundation for understanding motion. They're based on force and inertia. Remember, force is what causes objects to accelerate or change their motion, and inertia is the opposite. Inertia is an object's resistance to changing its motion. So how these two things interact, literally like a push and a pull or a yin and a yang, right? The way that they are interacting with each other, this creates motion. Okay, this is number 3 in your notes. Give me a green check when you have that saved. Green check when you have that saved. About 15 more seconds. Thank you. All right, let's match these up. Let's make sure that we understand these. Grab your whiteboard tools. Please match up the law with its definition. Match up the law with its definition. Remember, we talked about the first law yesterday. We talked about our second law, which is the equation, and the third law, that's what we just went over. Grab your whiteboard tools, put your answers up there. Perfect. 5, 4, 3, 2, 1, and 0. Uh-oh, what happened over here? We went a little bit crazy over there. All right, let me go ahead and shrink this down, make sure that we understand this. This is number 4 in your attendance ticket, so get your trigger finger ready to mark that down. Here we go. Newton's first law, object in motion will stay in motion with the same velocity unless acted upon by an outside force. Second law, force equals mass times acceleration, or you can change around the equation to also be acceleration equals force divided by mass. And Newton's third law, for every action there's an equal and opposite reaction. Green checks when you have number 4 saved, and then I'm going to give you the link to the quiz and wrap us up. You guys have 30 seconds. Ready, set, go. All right, waiting on Angelina, Charles, Ciara, Dalen, Emilio, Eric, Jasmine, Maya, Mike, Nadia, Theodore, Tristan. Green checks, please, if you've got number 4 saved. Awesome. Okay, here we go. So here was our objective for today, right? Doing Newton's second law, talking about F equals ma. I will show you question 5 in a moment. We also did Newton's third law, talking about actions and reactions. Let me go ahead and get you the link to the quiz today. Again, all the things you did, everything next to a yellow square, a yellow attendance ticket square, those are the answers to your quiz. So keep your attendance ticket open with your saved answers. Have your quiz open right next to it and do them at the same time. Or sorry, do your quiz while looking at your attendance ticket at the same time, and then submit both of them at once. All right, guys, here is your last word. This is number 5 in your attendance ticket. Go ahead and put in the word space, and I will see you guys later. Bye, everyone.